You may remember at the beginning of General Chemistry 1, you looked at the solid phase, the liquid phase, and the gas phase at this microscopic level, which is just looking at the different atoms bouncing around and interacting with each other. Remember that the solid phase doesn't mean that there's no motion, just that the molecules are so tightly packed that they can only vibrate. There's the liquid phase generally has that flat kind of curved or flat surface along the top. You don't have stuff filling up the entire container, but there is still more motion than the solid phase. And we got one popping up in the gas phase right there. And then we have the gas phase where everything is bumping off of everything. And you notice the containers being filled. You may remember also from General Chemistry 1, you spent a whole chapter looking at gases, gas behavior, PV equals nRT, things like that. Well, this semester in General Chemistry 2, you're going to be focusing on the liquid phase. You're specifically going to be looking at a lot of solutions, but we're going to start with looking at liquids. What makes things on this microscopic scale a liquid? Why are some atoms and some groups of atoms liquids at room temperature and others are gases? You'll notice that neon right here, if you notice the temperature, it's quite cold, negative 246 as a liquid. So at room temperature, it doesn't want to be a liquid. You notice argon, again, quite cold to be a liquid. Oxygen, quite cold to be liquid-like. And then you've got water, and water at room temperature, it's a liquid. If you look at something like the molar mass of these on the periodic table, you'll see that neon over here is 20 on the right-hand side. If you go over to oxygen to the left, oxygen is diatomic, so it would be 2 of those 16, so that's 32. That's a little bit heavier. Argon's 40, so all of those are in that range, and they are all gases. So it's really interesting that water, which has 1 oxygen and 2 hydrogens, which only has a mass of like 18, it's really interesting that this tiny molecule, when most of the time tiny molecules are gas at room temperature, this tiny molecule isn't. Then we're going to look at one more little hint on this. We are going to look at a hint about the attraction between molecules. So I'm going to jump to right here, just this adjustable attraction. And I'm going to put this back in Celsius so it makes more sense. And right now we have a solid that has a strong attraction. So you'll see the bar on here. It's on the right-hand side. So it just means the atoms between them have some kind of strong attraction. And if we move it to the left, you notice now our solid is a little bit more floaty, but it's still somewhat solidy. But you'll notice it is slowly changing and moving into another phase. Look at that. So remember, with a strong interaction, and it takes a minute to see it, it's going to pull together into that solid phase. With the weak interaction, it pulls apart, and they're not attracted to each other, and they start to separate. Now let's move this up a little bit in temperature. We're going to keep our interactions weak. And if you'll watch that pressure, so we already are closer to the gas phase. Look at that. Doesn't take very much temperature at all, and we're in the gas phase. You can tell that too because that pressure monitor on there. And now look at what happens. Those are all weak, so there's not much attraction. But if I pull them over to a strong attraction, and these molecules are all starting to shift back to the liquid phase at this temperature. So there's something going on about the attraction between molecules that you're going to learn, and atoms that you're going to learn about.